right now I'm going to start talking about polar coordinates. Polar coordinates are just another way of measuring where a point is in the plane. So if we take a look over here, alright, you see an XY axis, just like you're used to seeing it. You see a point in the plane, just like you're used to seeing it. I can label that point if I want to, X, comma, Y. But there are other ways to describe where that point is sitting based on the XY axis. Alright, if I draw a line segment from the origin, we're going to pretend that's a straight line, to the point, then I can measure a distance from the origin to the point, and I'm going to call that distance R. I can also measure an angle from the x-axis to that line segment, and I'm going to call that theta. Right? So I can describe where this point is sitting in the plane by looking at the angle that the line segment from 0 to the point makes with the x-axis and the length of the line segment. Alright, so in our normal coordinate geometry, we would call that xy. In polar, alright, we would use r, comma, theta. Just like that. So, if I have a point in polar coordinates, let's say that I call 2, comma, pi over 4. Right, we'll measure this one in radians. And I want to see where that point is on the xy axis. Alright, I would... how about we draw a straight line? Let's at least try to draw a straight line. Alright, I would draw an xy axis. I would put the angle pi over 4 on the graph first, so that is 45-degree angle, so that comes right up the middle there, right? Pi over 4. And then I would count out 1, 2 on that line. Alright, so there is the point 2 comma pi over 4. So graphing points is easy as long as you can locate the angle. Alright, for some of you that may mean turning it to degrees, that's fine. So what else can we do with this? Let's see, what else do I have here in my notes? Okay. Something that is definite on the xy axis, right? Positive is on this side, negative is on this side. Positive is up, negative is down. It's a little different in polar because in polar I'm not measuring up, down, left, right. I'm measuring in a circle. Okay? And when I'm measuring in a circle, if you remember from our original discussion of angles way back when, alright, I gotta stop trying to draw straight lines without help. Alright, let's see, where am I here? Alright, so, okay. When we measure an angle in this direction, right, counterclockwise, the angle is measured positive. When I measure an angle this way, counterclockwise, it's measured negative. Alright, so that's how we deal with the angles. Dealing with R is a little tricky. Alright, I'm going to go to a blank sheet here so I can start again. So let's take, here we go. Let's take, really? Okay, let's take a straight line. I want to make a nice big one this time. Okay. Alright. The way you're going to determine what's positive and what's negative for R is where the angle lands, the terminal side of the angle, is always going to represent the positive polar axis. So, if I have, let's start with this point here. If I have the point well, all right, so we did 2 comma pi over 4. All right. I measure the angle first. I always measure the angle first. And I draw the terminal side of the angle in on the graph. That represents my positive r-axis. So in the case of pi over 4, right, I've got my pi over 4 angle, measuring it here. So this is the terminal side of the angle, so that is the positive axis. The negative axis is going to be, well, just like it is on the xy axis, 180 degrees in the other direction. So the negative axis is going to come out this way, and this would be the negative axis. Okay? So the terminal side, right, the terminal side is always positive. Always plus for r. All right, wherever that terminal side lands, that's your positive axis. The negative axis is in the opposite direction. All right, so what if I wanted to graph the point negative 2 pi over 4? All right, well, I'm measuring my angle pi over 4 to here. All right, so that's my positive axis. So if I want negative 2, I have to go back this way 2. All right, and there is the location of negative 2 pi over 4. All right, so the terminal side of the angle is the positive r axis, the positive polar axis. All right, now, there are different ways to get to an individual point. All right, I have this point. We're going to stick with this point for now, okay? All right, I have that point that I graphed, and I graphed it using a radius of negative 2 and an angle of pi over 4. All right, suppose I want my angle theta to be, let's see, what do I want my angle theta to be? How about between negative 2 pi and 0? And I want my r to stay negative. All right, so, but I want to land on the same point. Okay, so here's the trick. We always go for the angle first. All right, so my angle has to be negative. That means I need to measure it in this direction. All right, I need to land, still need to land on the positive r axis there. All right, so what is that going to be? That's going to be negative 7 pi over 4. Right, 1, 3, 5, 7, yes. Negative 7 pi over 4. All right, so that still lands me here. This is still my positive r axis, so negative 2 is back here. All right, so I have another representation for this point, negative 2, negative 7 pi over 4. So I've already got two representations of the exact same location. All right, there are more. What if I wanted my radius to be positive? All right, suppose this time I want my theta to be positive between 0 and 2 pi. And I want my r to also be positive. But that point has to be in the same location. All right, so if I want my r to be positive, that means I want this to be the positive axis and this to be the negative axis. So when I measure my angle in the positive direction, I'm measuring it around to here. Okay, sorry, my pen's a little flaky here. All right. So if my point is going to be on the positive axis, this line right here has to be the terminal side of the angle. So I measure around to here, and that is 5 pi over 4. All right, and then my radius is going to be positive 2. All right, so here's another representation for these conditions where the radius is 2 and the angle is 5 pi over 4. All right, so there's lots of different ways to represent one individual point in polar coordinates. All right, so when you do your homework, make sure you're looking at the individual conditions for each problem. What they want r to be, what they want theta to be. You always go for theta first. You map out theta first. Where does theta land? What's the terminal side of theta? You draw that in, and that is your positive axis. Then you look at whether r is positive or negative, in which case you either move forward or backward, toward the positive or toward the negative. Right? All right, so these points have representations in polar and rectangular coordinates. All right, hang on, I need another axis here. All right, so if I have a point in polar coordinates, or I have a point in rectangular coordinates, and I want it the other way around. Well, we have formulas to move back and forth with. If I have a point, I'll put this point back right here, that is x, y. All right, we've already seen from our discussion of the unit circle and the earlier stuff in trigonometry that x is r cosine theta. Right? The x-axis is always cosine. And y, I'll write it over here, is r sine theta. So if I have a polar coordinate, all right, so we'll make this r 2 comma pi over 4. If I have a polar coordinate and I want to know what that is as a rectangular coordinate, I just have to drop r and theta into r and theta for x and y. All right, so r is 2 cosine pi over 4. All right, so that's going to be 2 times rad 2 over 2, or just rad 2. All right, so my x-coordinate is rad 2. Over here, r is 2. Sine of theta is rad 2 over 2. All right, so that is also rad 2. All right, so in polar, this is polar. In rectangular, this is going to be square root of 2, comma, square root of 2. All right. Now what if you want to go the other way? All right, if I have a point that in rectangular coordinates and I want to convert it to polar coordinates, well, again, we use the fact that we're working on circles, and r is representing the radius of a specific circle, so then r squared is going to equal x squared plus y squared, right? Not just circles, but circles centered at the origin. So r is going to be the square root of x squared plus y squared. For theta, you could use any of the trig functions, but typically we use tangent. All right, so we use the fact that the tangent of theta is y over x. All right, so theta is going to be tan inverse of y over x. All right. The only little catch with theta is just, remember the domain for inverse tangent is the first and fourth quadrant. So you're just going to have to look at the conditions on the problem, okay, and where the point lies. Use the inverse tangent to get a reference angle, and then if your point lies in the second or third quadrant, you just move to the angle in that quadrant. All right, so the conversion formulas that we're going to be using for this are right here. All right, to get r and to get theta. Okay. All right, now we can also convert equations back and forth. Polar form equations sometimes have an advantage over rectangular form equations in that something that is not a function in rectangular coordinates may actually be a function in polar coordinates. And you're going to need the ability to do that in calculus, because there are some things in calculus you can do with functions and some things that you can't do if you don't have a function. The conversion formulas back and forth are essentially the same as the point formulas. The important ones that you're going to need are x squared plus y squared equals r squared, and x equals r cosine theta, and y equals r sine theta. Okay. So if I have an equation in rectangular coordinates, all right, if I had the equation 4xy equals 9, and I want to convert this to polar form, all right, well, really all I have to do is substitute for x and substitute for y. That's easy. All right, r cosine theta, r sine theta, and that's equal to 9. And then just clean that up a little bit. All right, so I've got 4r squared cosine theta sine theta equals 9. All right, and I would just leave it like that. If you're going the other way, you may have to think a little bit harder. It's a little more involved to convert from polar to rectangular than it is from rectangular to polar, because it's not always just a matter of making a simple substitution like that. If I have a polar equation, suppose I have the polar equation r equals 6 cosine theta. All right, I have to find a way to work these equations backwards to x and y. All right, now I have an r and I have an r, all right, that involves x and y, but it's an r squared. All right, I have 6 cosine theta. What I need is r cosine theta. All right, since I need one side to be r squared and I need the other side to also have an r, it doesn't currently, I can multiply both sides of this equation by r, basically multiply the whole equation by r, and then I get r squared 6r cosine theta. So this is x squared plus y squared, and this is 6x. Okay. I'm not going to get into what that's the form of yet, because we're going to talk about conic sections a little bit later, but that would be good enough. All right, so I think that's all we need for polar coordinates right now, so I'm going to stop and go on to the next video.